In this section, we discuss the domain microstructure of ferromagnetic materials. Although all the spins in a small grain can be ferromagnetically aligned, larger grains often form subgrain domains, much like twins. We shall see that the magnetic domain boundaries can be moved with a magnetic field and pinned by defects like other types of microstructure studied in materials science. In a crystal, the magnetization prefers to be along a particular direction due to magnetocrystalline anisotropy, even in a cubic crystal. For example, BCC iron reaches its full saturation magnetization in a small applied magnetic field when it is along 100. We call this the easy direction. Magnetizing along 111 requires an additional magnetic field to rotate the magnetization from 100 to 111. In iron, 111 is the hard direction. When the field is removed, the magnetization will rotate back to the easy direction. A single domain produces a magnetic field outside the material which stores magnetic energy. The formation of two regions with opposing spins reduces the external magnetic field, but requires the formation of a domain wall. The formation of more domains can further reduce the external fields. There may be several domains where there is no external field produced. Such material is said to be demagnetized. A demagnetized material has opposing domains that exactly cancel. When an external field is applied, the domain walls move to enlarge domains align with the field and shrink those opposing the field, resulting in a net magnetization. The domain walls themselves are not usually atomically abrupt. A gradual rotation, such as the block wall of several hundred atoms, has lower energy by keeping neighboring atomic interactions largely ferromagnetic. When a material is magnetized, it produces a small amount of strain called magnetostriction. Although small, it leads to some inhibition to magnetization and demagnetization due to strain energy. The movement of domain walls is also inhibited by defects, similar to how grain boundary motion is inhibited by defects. Any strain at a domain wall due to magnetostriction will couple to the strain of a dislocation and then become pinned there. Similarly, impurity phases can pin domain walls by reducing their magnetic or magnetostriction energy. A polycrystalline magnetic sample will generally have domain boundaries as well as grain boundaries, particularly in large grains. The striped domains are visible using a Kerr microscope. The magnetization of most of these domains are in plane, like in the schematic, except for the outline grain where M is vertical. Grain boundaries will also aid at pinning domain walls, hindering their movement. When a demagnetized sample is placed in a magnetic field, the magnetization increases first by domain motion. Some domain motion is unhindered and easily reversed. Some occurs in jumps because of domain pinning, which makes it less reversible. The domains magnetize along the easy direction first. After the grains become single domain, further magnetization along the field direction requires the magnetization to rotate out of the easy direction. When the magnetocrystalline anisotropy energy is overcome, the saturation magnetization is reached. As the magnetic field is reversed, the magnetization first rotates back to the easy direction, then some opposing domains may form due to the demagnetizing effects of the specimen. Some magnetization will remain even in zero applied field. This is called the remnant magnetization. Applying a magnetic field in the reverse direction will be needed to reduce the magnetization to zero. This is called the coercive field. The pinning of domain wall motion leads to the curves for increasing and decreasing field to be different, which is called hysteresis. The M or B versus H curve is often called a hysteresis curve. Recall that for a ferromagnet, M is much bigger than H, so that B is approximately a measure of M. A full hysteresis curve is measured from full saturation to reversed saturation. The area enclosed in the hysteresis loop is the energy absorbed by the ferromagnet to move the domains past the pinning sites, ending up as heat. Magnetic hysteresis loops can be wide or narrow. A hard magnetic material has a wide hysteresis loop because of a large coercive field which is needed for a strong permanent magnet. Hard magnets usually have high magnetocrystalline anisotropy to keep the magnetization along a particular crystallographic direction. Also, because defects and microstructure pin the domain motion that would demagnetize a magnet, the hardness of a magnet depends on the composition, impurities, and processing. A soft magnetic material changes its magnetization easy and therefore induces a large magnetic B field from a small applied H field with little hysteresis loss because of its low coercive field. Soft magnets can be made from cubic ferrites, while anisotropic hexagonal ferrites make good hard magnets. Because soft magnetic materials produce a large magnetic field from a small applied field, they will induce a large current in a secondary loop, moving magnetic energy from one loop to the other. With a different number of windings in each loop, the electrical energy is transformed from one voltage to another. Transformers are used to step up or down voltage in power transmission and electronics. Some electronics require an inductor circuit element, which is simply a coil around a soft magnetic material which greatly increases its inductance. Low hysteresis in a soft magnet reduces the electrical loss in both applications. Hard magnetic materials have a wide hysteresis loop characterized by a large coercive field Hc and a large remnant magnetization, here B sub r. The magnetic energy density of a hard magnet is characterized by Bh max. Neodymium iron boride is a relatively new magnetic material with a very high Bh max. Many of the new hard magnets in use today contain rare earth elements such as neodymium and samarium and are called rare earth magnets. The much stronger and smaller rare earth magnets have made motors and generators more powerful, efficient, and compact, which has helped speed the transition to electric vehicles and renewable electricity. They are also used in high-performance consumer products such as speakers and earphones. Magnetic recording is still the primary method to store large amounts of data. Data is stored as small regions of magnetic domains written in a thin film of hard magnetic material. Data density now exceeds 1 terabyte 10 to the 12 per square inch at a consumer cost of 3 cents per gigabyte. Soft magnets are used for writing the data. A magnetoresistive sensor is used to read the data.